This is part 3 of a series on LightGBM. In this video, we will look at the EFB algorithm called exclusive feature bundling and the greedy bundling algorithm. This video was produced in Korean and translated into English, and my voice was generated through AI text-to-speech. In the last video, we looked at the gradient-based one-side sampling algorithm and implemented it as code. In this video, we will analyze the greedy bundling algorithm for exclusive feature bundling and implement it as code. In section 4 of the LightGBM paper, exclusive feature bundling and merge exclusive features algorithms are proposed. This section proposes a novel method to effectively reduce the number of features. In the data below, the 5 features are reduced to 3. High-dimensional data are usually very sparse. The data below also contains a lot of zeros. The sparsity of the feature space provides us a possibility of designing a nearly lossless approach to reduce the number of features. Specifically, in a sparse feature space, many features are mutually exclusive, i.e., they never take non-zero values simultaneously. In the data below, for features F1 and F2, these data points never have non-zero values at the same time. Here, only one data point has non-zero values at the same time. We can safely bundle exclusive features into a single feature, which we call an exclusive feature bundle. By a carefully designed feature scanning algorithm, we can build the same feature histograms from the feature bundles as those from individual features. There are 2 issues to be addressed. The first one is to determine which features should be bundled together. This is the greedy bundling for exclusive feature bundling. The second is how to construct the bundle. This is the merge exclusive features. Exclusive feature bundling uses the graph color problem. Graph coloring refers to the problem of coloring the vertices of a graph so that the colors of 2 adjacent vertices are not the same. In this video, we'll look at the greedy bundling algorithm. The merge exclusive features algorithm is discussed in the next video. When feature values simultaneously take on non-zero values, this is called a conflict. In the figure below, for features F0 and F1, these data points have non-zero values at the same time. This is called conflict. Otherwise, they are mutually exclusive. For features F1 and F2, most feature values have at least 1 zero. Exclusive features can be bundled into a single feature. In the example below, the number of conflicts between features F0 and F1 is 6. For features F1 and F2, the number of conflicts is 1. Here is one. Features with few conflicts can be bundled together. First, create a conflict count matrix. The number of conflicts between F0 and F1 is 6. And the number of conflicts between F0 and F2 is 2. There's one here, and there's another here. In this way, we create a conflict count matrix. Next, sort the sum of the conflict counts in descending order. This is the sum of the conflict counts and sort them in descending order as follows. Feature F4 has the largest number of conflicts. We can create a graph like this before creating a conflict count matrix. The number of conflicts between F4 and F3 is 3. Nodes or vertices are features and edges are conflict counts. Let's look at the algorithm 3 presented in section 4 of the paper. F stands for feature, and K is the maximum number of conflicts. Construct graph G using the feature values. In this algorithm, conflict count is called degree. Sort the conflict count matrix by degrees. This is search order. This is the table at the bottom right. Then, feature bundling is performed by exploring search order one by one. This process will be discussed on the next page. The source of this example is this video by Professor Pilsung Kang in Korea University. Set the maximum number of conflicts K. In the example below, set it to 1. Before analyzing the algorithm 3, let us first briefly review this process with a simple example. Graph G and search order tables created on the previous page are as follows. In this graph, we remove the connections with conflict counts greater than 1, which is max K. The results are as follows. F3 and F0 are connected, and F2 and F1 are connected. Since F3 is already connected to F0, this connection is removed. Then, 3 bundles are created like this. F0 and F3 can be combined into one bundle, and F1 and F2 can be combined into another bundle. This is the greedy bundling algorithm. As a result, 5 features are bundled into 3. Now let's analyze the algorithm 3 step by step. Read the features one by one from the search order table. Initialize the need new variable to true. And initialize the bundles list and the bundles conflict list. Initially, they are all empty. Next, read the features F one by one from the bundles list. This is the bundles list. Because it's empty at first, these steps are skipped. Next, since the need new variable is true, fi is added to the bundles list. Currently I is F4, so the F4 feature is added to the bundles list. And 0 is added to the bundles conflict list. This is the bundles conflict list, and 0 has been added. In the next iteration, I is F0. And J is from 1 to 1. This is because F4 has been added to the bundles list. And get the conflict counts between F0 and F4 from the graph. The count is 6. And add the jth element of the bundles conflict list to this value. This is 0. If it's less than K, perform this process. However, since this condition is false, these steps are skipped. In the next step, since the need new variable is still true, F0, which is Fi, is added to the bundles list. And another 0 is added to the bundles conflict list. In the next iteration, I is F1. And J is from 1 to 2. This is because there are 2 elements in the bundles list. If J is 1, get the conflict counts between F1 and F4 from the graph. That is to get this count. This is also 6. To this value, we add 0, the jth element of the bundle's conflict list. This is also not less than k, so these steps are skipped. If true, then fi is f1 and the jth element in the bundles list is f0. Get the conflict counts between f0 and f1. This is also 6. To this value, we add 0, the jth element of the bundle's conflict list. This is also larger than k, so these steps are skipped. And since the need new variable is still true, we add f1, which is fi, to the bundles list. Add 0 to the bundle's conflict list. In the next iteration, I is f2. J is from 1 to 3. This time, there are 3 elements in the bundles list. If J is 1, get the conflict counts between F2 and F4 from the graph. The conflict counts between F2 and F4 is 4. To this value, we add 0, the jth element of the bundle's conflict list. This is also larger than k, so these steps are skipped. If J is 2, get the conflict counts between F0 and F2. The conflict counts of F2 and F0 is 2. To this value, we add 0, the jth element of the bundle's conflict list. This is also larger than k, so these steps are skipped. J is 3. Get the conflict counts between F1 and F2. The conflict count of F2 and F1 is 1. To this value, we add 0, the jth element of the bundle's conflict list. This is equal to k. So this time these steps are performed. Add F2, which is fi, to the jth bundles list this way. The third space contains 2 elements. This is what .add means. And update the need-new variable to false. Then add the CNT variable value 1 to the jth element of the bundle's conflict list. The third element in the bundle's conflict list is then updated from 0 to 1. Handling F3 in this way puts F3 in the second space in the bundles list. The final result of the bundles list is like this. F4 is one bundle. F0 and F3 are bundled together. F1 and F2 are bundled together. That's the result. This is how the algorithm 3 works. Algorithm 3 in the paper has typos and some missing parts. Modified them with red text. Now let's implement the greedy bundling algorithm as code. The data we will use is like this. It was used in the previous page example and has 5 features. First, create a conflict count matrix like this. The procedure is as follows. I will omit the detailed explanation. Next, we calculate the sum of the conflict counts. This is the degree. Sort the degrees in descending order. This is the search order table. Set the max conflict counts k to 1. Initialize the bundles list and the bundles conflict list. Next, we read the features one by one from the search order table and perform the following steps. This code is written as is for this algorithm. This process was explained in detail on the previous page, so the explanation will be omitted here. Let's check the results. You can see that the features are bundled like this. Let's try to run this code. The results came out like this. The conflict count matrix is like this, and the search order table is like this. And the features are bundled like this. So far, we've analyzed the greedy bundling algorithm and implemented it as code. In the next video, we will look at the merge exclusive features algorithm and implement it in code to complete the exclusive feature bundling.